Welcome students. Welcome to St. Joseph's open web-based learning platform. So we learn for a soulful and enriching e-learning experience. Welcome students. Welcome to Department of Mathematics. You are welcome to second semester mathematics course differential equations. This course is divided into 5 units and now we are going to learn about unit 3 higher order linear differential equations. The instructor for this unit is Sunita Chaudhary, Assistant Professor, Department of Mathematics, St. Joseph's College for Women, Autonomous, Vishakhapatnam. The first chapter of this unit is Solutions of Homogeneous Linear Differential Equations of Order n with constant coefficients. Learning outcomes. By the end of this chapter, the learner should be able to find solutions of homogeneous linear differential equations of order n with constant coefficients. This unit, that is higher order linear differential equations, is divided into two chapters. And the first chapter is solutions of homogeneous linear differential equations of order n with constant coefficients. The content of this first chapter are basic introduction, next definition and symbolic form of higher order linear differential equations with constant coefficients. Next, learn about homogeneous linear differential equations of order n with constant coefficients, and find solutions of homogeneous linear differential equations of order n with constant coefficients in different cases arises while solving the auxiliary equation. And finally, some practice problems are given for learners to practice. Let's begin this chapter with some basic definitions and their examples. First definition, differential equation. It is an equation which involves derivatives of one or more dependent variables with respect to one or more independent variables. Let's see some examples of differential equations. First example, dy by dx is equals to x plus sin x. In this example, the equation involves first order derivative of one dependent variable y with respect to one independent variable x. Second example, fourth derivative of y with respect to x plus 3 times second derivative of y with respect to x plus first derivative of y with respect to x plus 2 times y is equals to 0. In this example, the equation involves derivatives of one dependent variable y with respect to one independent variable x. Third example, dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square is equals to 0. In this example, the equation involves derivatives which are partial derivatives of one dependent variable u with respect to three independent variables x, y and z. Thus, these are some examples of differential equations. Next definition, ordinary differential equation. It is an equation which involves derivatives of one or more dependent variables with respect to a single independent variable. Let's see some examples of ordinary differential equations. First example, dy by dx is equals to x plus sin x. Second example, fourth derivative of y with respect to x plus 3 times second derivative of y with respect to x plus first derivative of y with respect to x plus 2 times y is equals to 0. In these two examples, the equation involves derivatives of one dependent variable y with respect to a single independent variable x. Now third example, dx by dt plus dy by dt is equals to 2x plus y. In this example, the equation involves derivatives of two dependent variables x and y with respect to a single independent variable t. Thus, these are some examples of ordinary differential equations. Next definition, order of the differential equation. It is the order of the highest order derivative involved in a differential equation. Let us see some examples. First example, in this example 1, the highest order derivative involved in the equation is d square y by dx square. So, the order of the differential equation is 2. Second example, in this example 2, the highest order derivative involved in the equation is d cube y by dx cube. So, the order of the differential equation is 3. Next definition, degree of a differential equation. It is the power of the highest order derivatives which occurs in the differential equation. Remember, to define degree of a differential equation, the differential equation must be a polynomial equation in derivatives. Let's see some examples. First example, in this example 1, the highest order derivative involved in the equation is d square y by dx square, whose power is 2. So the degree of a differential equation is 2. Second example, in this example 2, the highest order derivative which involved in the equation is d cube y by dx cube, whose power is 1. So the degree of a differential equation is 1. Next definition, linear differential equation. It is an equation which satisfies the following two conditions. First condition, every dependent variable and every derivative involved in the equation occurs in the first degree only. It means in the equation, all the dependent variables and its derivatives must have degree 1. Second condition, no products of dependent variables and or derivatives occur in the equation. It means the equation should not contain product of dependent variables and or product of derivatives and or product of dependent variables and its derivatives. The equation which satisfies these two conditions is said to be linear differential equation. Let's see some examples. First example, dy by dx is equals to x plus sin x. In this example, the equation involves only one derivative, dy by dx, whose power is 1. And dy by dx is not multiplied with the dependent variable y and its derivatives. So this is an example for linear differential equation. Second example, d cube y by dx cube plus dy by dx plus y is equals to 0. In this example, the dependent variable y and its derivatives dy by dx and d cube y by dx cube have degree 1. Also, the dependent variable y is not multiplied with any other derivatives. The derivative dy by dx is also not multiplied with dependent variable y and any other derivatives. Also, d cube y by dx cube is not multiplied with dependent variable y and any other derivatives. So this is an example for linear differential equations. Thus, these are some examples for linear differential equations. Let us see the definition of higher order linear differential equations with the constant coefficients. Definition, a differential equation of the form an times nth derivative of y with respect to x plus an minus 1 times n minus 1th derivative of y with respect to x plus so on plus a1 times first derivative of y with respect to x plus a0 times y is equals to q of x, where q of x is the function of x only and a0, a1, so on, an are all constants which are coefficients of dependent variable and its derivatives respectively with an not equals to 0. The equation of this form is said to be linear differential equation of order n with the constant coefficients. Let us see one example. dqy by dx cube plus 6 times d square y by dx square plus 11 times dy by dx plus 6 times y is equals to e power 2x. Here, e power 2x is the function of x only. And here, dqy by dx cube is the highest order derivative in the equation. So, the order of the equation is 3. And here, the coefficients of the dependent variable and its derivatives are numericals, which are constants. Thus, this is an example for linear differential equation of order 3 with constant coefficients. Let us see what is meant by homogeneous and non-homogeneous linear differential equations of order n with constant coefficients. Here I denoted linear differential equation of order n with constant coefficients with small a. In this equation, when q of x is equals to 0, then the equation is referred to as homogeneous linear differential equation of order n with constant coefficients. When q of x is not equals to 0, then the equations are said to be non-homogeneous linear differential equation of order n with constant coefficients. Now let us convert higher order linear differential equations with the constant coefficients in symbolic form. For this, we introduce a differential operator capital D, which simply represents the operation of taking an ordinary differentiation d by dx. For a function y is equals to f of x, the differential operator d transforms the function y to its first order derivative dy by dx. So, dy is equals to dy by dx. d square y is equals to second derivative of y with respect to x, and so on. We get d power n y is equals to nth derivative of y with respect to x. Now substitute these values in the differential equation A, that is an times nth derivative of y with respect to x plus an minus 1 times n minus 1th derivative of y with respect to x plus so on plus a1 times first derivative of y with respect to x plus a naught times y is equals to q of x becomes an times t power ny plus an minus 1 times t power n minus 1 y plus so on plus a1 times dy plus a naught times y is equals to q of x. In this equation here, nth derivative of y with respect to x is replaced with d power ny. Also, n minus 1th derivative of y with respect to x is replaced with d power n minus 1y. Like this, so on. First derivative of y with respect to x is replaced with dy. Thus, we get the equation an times d power ny plus an minus 1 times d power n minus 1y plus on plus a1 times dy plus a naught times y is equals to q of x. Now in this equation, from the left hand side, we can take out common y. Thus we get the equation n times d power n plus n minus 1 times d power n minus 1 plus so on plus a1 times d plus a naught of y is equals to q of x. Now in this equation, the bracket term is denoted with f of d. Thus we get the form f of dy is equals to q of x, where f of d is equals to n times d power n plus n minus 1 times d power n minus 1 plus so on plus a1 times d plus a naught. Thus, f of dy is equals to q of x is the symbolic form of the differential equation. Thus, f of dy is equals to q of x is the symbolic form of the higher order linear differential equation of order n with constant coefficients. In the next video, let's see the procedure to determine the general solution of homogeneous linear differential equation of order n with constant coefficients. Let's see what we have learned. We learn about higher order linear differential equations with constant coefficients, and its a symbolic form. We will meet in the next video lecture, students. Thank you.